Hey everyone, what we're going to be looking at today is to help you with a resource pack assignment number 8, which is entitled Colligative Properties. I know that sounds weird and odd, but really all it's talking about is how is water affected when we start dissolving stuff in it? How easy is it for its particles to move around in the way that they're used to? So let's take a look at these two scenarios that I have drawn out here. On the left, we've got pure H2O, or at least a model of it. This pure H2O is wanting to boil. So that's what this arrow is representing. In order to boil, this liquid particle needs to be able to escape out into the gas phase. Now, this happens on and off, and that's what generates vapor pressure. But if we're going to boil, we've got to get all these molecules from the liquid stage into the gas phase. And in order to do that, the water needs to overcome the intermolecular forces holding it together. Because this is water, that means overcoming hydrogen bonds. It's not the easiest thing in the world, but it does happen once we hit 100 degrees Celsius at standard pressure. If we move over here to the left, what I'm going to do is dissolve some NaCl in the water. And you know that NaCl will dissolve to create positive Na ions and negative Cl ions. In this case, all I'm going to do is just draw out the two ions that NaCl is going to create in water. And even by doing that, just visually, what you see is if this same water molecule wants to boil, it now has a new obstacle in its way. And it might be a little bit harder for this molecule to be able to escape from its liquid phase into the gas phase. Now, this isn't 100% what's happening in solution, but visually, it's a very easy way to think about it. This is now harder to boil, so we need to get those water molecules moving faster and faster if they're going to be able to jump out of solution and into the gas phase. So what we see when we dissolve stuff in water is that the boiling point increases. It takes more energy to boil the water, so it happens at a higher temperature. Now, this is only going to increase if, let's say, I dissolved more particles. Instead of dissolving NaCl, let's dissolve calcium chloride, CaCl2. That gives us not just 2 particles, but a third particle that we're able to work with. What you see now is that there's more stuff getting in the way, so the boiling point would go up even more. If we look at sort of the opposite end of the spectrum, the freezing point, what you're going to notice is that in order to freeze, water molecules need to sort of come together in an orderly fashion. They need to align just right so that they're in this nice geometric pattern. That's okay for these water molecules to do. If we slow them down enough, they're going to be able to align their hydrogen bonds so that we can form ice. Over on this side, though, we've still got these particles in the way. Now, not only do these water molecules have to align themselves appropriately, they've got to align themselves so that this junk isn't getting in the way and they're still happy and all those particles are arranged perfectly. That's just a lot to think about, so we're going to have to slow the molecules down even more if we want that process to be able to happen, just because there's stuff in the way. So what we see is that the freezing point decreases. And just like we saw before, by adding this extra ion, we could hypothetically decrease the freezing point even more if we threw even more ions, more particles into the way of these water molecules being able to align. And that's what this business down here is about. If you want to create a bigger disturbance in boiling and freezing point, you can do it one of two ways. Let's say we've got NaCl. If I dissolve enough NaCl in water to create a 1 molar solution, we know we're going to knock the freezing point down a bit. But if I dissolve enough salt to create a 2 molar NaCl solution, that's going to knock the freezing point down even more, because concentration is just a representation of how many particles you've dissolved in water. This solution has more NaCl particles, which means more stuff to get in the way of the water either freezing or boiling. So this solution, compared to this one, will have the higher boiling point and the lower freezing point because there's more particles there. Not too bad. The second consideration can sometimes give some people trouble because it necessitates that you understand electrolytes. You understand how ionic compounds, acids, or bases break apart in water, and when they do, how many ions they form. So let's take our 2 molar NaCl solution and compare it to a 2 molar CaCl2 solution. We've already kind of got at this point, but let's break it down just a bit further. We see that the concentrations are exactly the same, so we can't judge based on concentration. We're going to need to judge who has the higher boiling point and the lower freezing point based on number of ions. And in this case, Na is going to be your positive part of this electrolyte, and Cl is going to be your negative part. I've drawn 2 ions, so this has a total of 2 particles that it will break apart into. If I look at CaCl2, I now see that my metal is still going to take on the positive charge, and I've got 2 chlorines that are going to be able to each create a -1 charge. That's a total of 1, 2, 3 particles. More ions, more particles, a bigger disturbance. This is going to boil at the higher temperature and freeze at the lower temperature. The only thing that can sort of be used as a distraction is a covalent compound that's not going to break apart at all. So let's take a solution like a 2 molar solution of, let's say, sugar. And typically when we talk about sugar, we're usually talking about glucose. So let's look at that. If I try and apply the same logic as I did up here, I'd be trying to break sugar apart into a positive and negative piece. And if you try and do that, what you're going to find is there is no positive piece that makes sense. You're not going to break this into C6 and H12O6. You can't break it apart between the C and the H. You just can't break apart sugar, and that's because it's covalently bonded. It's not an acid. There are no ions that it's going to create when it dissolves in water because it's a covalent compound that's not going to break apart. So this whole thing stays as one unit. So it represents only one dissolved particle, which means even salt water will boil at a higher temperature than sugar water. I hope this helps with this idea of colligative properties, or what happens when you dissolve stuff in water, and that it helps with assignment number 8 in your resource pack and a handful of questions on your practice test.